One by one, we have to discuss all these greenhouse gases. The very first greenhouse gas that you can see in your screen is the H2O. Yes, H2O in vapor. So in the vaporized form, this is very, very prone greenhouse gas. It accounts for 60 to 90% of the greenhouse effect, while CO2 only contributes 25% of the greenhouse gas. So you can see that how much contribution is there by this H2O vapor. And here the lambda absorbance range of all the different greenhouse gases is important that you have to remember. So if you look at the water vapor molecule, it absorbs the radiation in the range of less than 8 micrometer and more than 18 micrometer. This is only the two zone where the H2O absorbs radiation or energy and causes the warming of the Earth's surface. And coming to the CO2 pre-industrial era concentration, we know that is 280 ppm. Right now, the concentration is about 417 to 419 ppm. So in this range, the CO2 concentration is continuously fluctuating. Lambda absorbance range is 4 to 5 micrometer in the case of CO2. So you can see less than the H2O, it will absorb the radiation, and in the range of 14 to 19 micrometer, or exactly in between 13 micrometers, so it absorbs the long wave radiation. Then we can talk about the sink of CO2. So sink of CO2 is the CO2 where the CO2 is kept abundantly. So very abundantly, you can find CO2 in the ocean. So in the ocean, it is well dissolved. Then after ocean, the highest amount of CO2 is found out you can in the forest. In the forest, it is stored in the form of biomolecules. So those forests are having huge amount of CO2. And last is it is mainly in the soil. And after soil, the the fourth largest pool of the CO2, sink of the CO2 is our atmosphere. Then here you have to remember that we have total 417 or 419 ppm of CO2 in our atmosphere, and 1 ppm of the CO2 in our atmosphere is equals to 2.12 gigaton of CO2. So this is the exact calculation you can say. So these are the values you have to remember that 1 ppm of CO2 in the atmosphere equals to 2.12 gigaton. Gigaton is 10 to the power how much? 10 to the power 9 ton of this CO2. So you have to remember it also the giga meaning here 10 to the power 9. So I hope it is clear. Let's see some questions asked from this particular section. If CO2 concentration now is suppose 480 ppm, calculate the amount of CO2 added in kg after the pre-industrial era. So suppose there is a hypothetical situation that CO2 concentration reaches to 480 ppm. So here this would be 480 ppm right now. The pre-industrial era was around how much? 280 ppm. So the 200 ppm of CO2 is added now in the atmosphere, and 1 ppm is equals to 2.12 gigaton. So 200 multiplied by 2.12 gigaton. So this much amount of CO2 is now added in the atmosphere, that is equals to around 420. For the approximation, you can say 420 gigaton of CO2 is added. So this would be 4.2 multiplied by 10 to the power 9 for the gigaton, and this is 4.2, 2 more will become there. This is 4.2 multiplied by 10 to the power 11 ton. To convert it into kg, again 1000 you have to multiply. That would be 4.2 10 to the power 11 plus 3 10 to the power 14 kg of CO2 is added after the pre-industrial era. So this is how you can calculate the amount or weight of CO2 present in the atmosphere. So 480 minus 280, 280 was the pre-industrial era. So after that it is equals to 480 minus 280, 200 ppm. 200 ppm you have to multiply here. 200 ppm is equals to 2 point multiplied by 2.12 gigaton, that is around 420 gigaton, that is 4.2 multiplied by 10 to the power 11 ton, that is 4.2 multiplied by 10 to the power 14 kg of the CO2 that is added in the atmosphere after the pre-industrial era. So I hope it is clear to you. Next question is already asked question in the examination. If we add 500 million tons of CO2 in the atmosphere, so now calculate how much increase there would be in the terms of ppm in the atmosphere. So just convert this 500 million ton into gigaton. So 500 million ton is 500 multiplied by 10 to the power 6 ton. That is clear. So now this is equals to 5 multiplied by 10 to the power 8 ton. This is multiplied by 10 to the power 9 to convert it into gigaton. So that would be equals to 0.5 gigaton, right? This 0.5 gigaton divided by 2.12 gigaton. So this is the concentration of the CO2 in ppm that is added in the atmosphere. So if you just divide it, you will get this D option, 0.236 ppm. Because why? Because 1 gigaton is equals to 1 ppm. 2.12 gigaton is sorry is equals to 2.12 1 ppm here, 2.12 gigaton. So 5 gigaton is 0.5 gigaton is 0.5 divided by 2.12, that is equals to 0.236 ppm. So this is how you can convert the ppm to gigaton and gigaton to ppm easily. So I hope it is clear to you, and now we can move ahead. Next thing is the CH4, methane. So sink of CH4 that we have already seen in the reaction of the hydroxyl radical, OH radical. So CH3H react with the OH radical, it will create H2O by reacting in this portion. So by the reaction of this H2O and this CH3 would be converted into CH3 radical. This will again created with the reacted with the O2 and create CH3O2. This CH3O2 react with the NO and it will create the NO2 and CH3O. So this reaction continues in the atmosphere, and this NO2 which is created here, that particular NO2 will again go in the atmosphere and create ozone in the troposphere. That reaction also we have seen. So CH4 is not only directly participating in the reaction of the or global warming, you can say the increase in the temperature of Earth, but also indirectly it is creating nitrogen dioxide, which is ultimately again creating tropospheric ozone, and ultimately that tropospheric ozone will also increase the temperature of Earth, because tropospheric ozone is also greenhouse gas, you can see. Now, the lambda absorbance range of the CH4 methane is in 3 to 5 micrometer. Again, remember these values. These values are very, very important. Multiple times already asked in the examination. 3 to 5 micrometer, this is absorbing radiation, and then 7 to 8.5 micrometer in this range, this is absorbing the radiation. Residence time of the CH4 in the atmosphere, or lifetime, that we have seen in the previous table, that is 12 plus minus 3 years of the time period. Then the next gas we have to discuss is the nitrous oxide. Nitrous oxide, N2O. Sink of N2O, no sink of N2O present in the atmosphere, because this is not reactive at all. It is not reacting with any other gases. So no sink of the N2O is available in the atmosphere. Then lambda absorbance range of this N2O is again 3 to 5 micrometers, similar to CH4 and similar to this second value as well, 7.5 to 9 micrometer. So this is the range of the electromagnetic radiation absorbance of the nitrous oxide, N2O. So I hope these two gases are also clear to you. Next greenhouse gas that we have to discuss is the ozone. When the ozone lambda absorbance range is 9 to 10 to the power 10.6 micrometer. It is not absorbing any radiation of the short wave. This is only absorbing the long wave radiation that you can see here. And this is the property of the tropospheric ozone. This ozone is not stratospheric. Again, I am repeating, the greenhouse gases we are talking here about, that is the tropospheric ozone only, not stratospheric. And halocarbons, if you look at the halocarbons, the next greenhouse gases, So the halocarbons also don't have any kind of sink in the atmosphere. The region is same. These are also very stable and not reacting with the any other compound. So because these are stable, no sink is available of the halocarbons as well. The halocarbons are divided in five different categories. First one is the CFC, chlorofluorocarbon. After using the chlorofluorocarbon, we have witnessed the ozone hole formation, and due to that, chlorofluorocarbons are completely banned, and then we have introduced the hydrochlorofluorocarbon. Here, one chloro or fluoro is replaced by the hydrogen here. This is less harmful as compared to the CFC, but still well harmful for the ozone present in the atmosphere. So we banned the CFC as well. Then we have created the HFCs. HFCs are hydrofluorocarbons. Fluorine we have completely eliminated, and currently we are using these as HFCs as well, but in the very limited amount as well. Soon we will replace this HFC with the any other important molecule also. Then we have the perfluorocarbons. Perfluorocarbons are having only fluorons with them. And then we have the halogens. In halogens, the compound can be anything. It can be reacted with the bromine, chlorine, fluorine, any halogen is present there. That's why this is called as the halogens. If you look at the ozone depleting potential, so that's why we have removed chlorine, because chlorine is having more potential in the case of ozone depletion as compared to the fluorine. So we have first bromine, then chlorine, then fluorine. So this fluorine is here least harmful as compared to the other two gases. So that's why the fluorine here is pretty widely used as compared to the bromine and chlorine. And bromine is having the highest ozone depletion potential among all the halogen gases. I hope this is clear to you.